my name is Sandrine van Frank. As Robert said, I'm head of Terahertz technology at RECENTT. And what I'm going to present today are mostly results from the project PSSP, photonic sensing for smarter processes. In this project, we worked mainly on a novel approach for computed tomography based on terahertz radiation. But I'm also going to give a talk generally about fast terahertz imaging in the context of non-destructive testing. So here's the outline of my talk. I will start with some basic notions about terahertz. I'm not sure if that is really necessary regarding the results of the polls, but nevertheless, I will give it. So what is terahertz and what it can do for non-destructive testing? Then I will talk about terahertz for computed tomography and dive into our results on this topic in the project PSSP. And finally, as I said, I will talk about more broadly fast terahertz for industry, so industrial terahertz systems. Okay, so what is terahertz? If some people have heard only once about terahertz, then probably in the context of security, because that made the headlines. There are a few airports at which Terahertz scanners are installed that can detect weapons or other dangerous objects that could be carried around by passengers. It's not the only possible application of terahertz radiation. I will start with like a definition of terahertz. Terahertz is actually part of the terahertz of the electromagnetic spectrum, located between the microwave in the lower frequency part and infrared radiation. And the definition varies a bit, but we talk about terahertz radiation for the band that's roughly between 0.1 terahertz and 10 terahertz, or in terms of wavelength between 30 microns and 3 millimeters. And in terms of technology, this terahertz range here is actually between the realm of electronic devices and the realm of photonic devices, for both of which there are already many devices, applications developed. As you can see on this graph, in the frequency range corresponding to terahertz, it's not really the case. There are no mainstream application yet. There's actually a common phrase for that. It's the terahertz cap. The reason for that is that smaller, more compact sources or detectors of terahertz radiation only started being developed in the mid-80s, and new convenient sources or detectors are only now reaching a certain maturity that it can be used for non-destructive testing. So there are interesting properties of terahertz. One is that you can see through many opaque materials, many relevant to non-destructive testing, such as plastics, and also composites or ceramics, glass, wood, paper, semi-dry food. In these materials, you can then detect hidden features, void, inclusions, layer structures, delaminations, these kind of things. And you can do that in a way that is without contact and non-destructive. Another aspect of terahertz, which is interesting, is that you can do spectroscopy with it and have terahertz specific spectroscopic information for some things. For example, you can analyze crystal polymorphs and being able to identify and see the difference between different crystal polymorphs, which can be difficult with other wavelengths. And finally, it's a low energy radiation, which is also interesting. There are, of course, some limitations, like all technologies. One is that water and metallic materials do not let terahertz radiation through. So this can be a limit for applications. It can also be something that is interesting in some applications. As we saw in the very first example of security, you can detect weapons or other reflecting objects quite well. So here are some examples of things we looked at and measured in the past. On On the left side, some imaging applications. In one case, we looked at fiber reinforced plastics, and we could show that we can analyze the orientation of fibers locally in the sample. In another example, we did quality control in an adhesive layer. The adhesive layer was between a metal cylinder and a plastic plate that was not transparent in the visible range. And as you can see on the red, black and red image there were two air bubbles in the adhesive layer that we can detect efficiently with terahertz radiation. And in another example, a multi-layer pipe, we could measure the layer thickness of the different layers in this pipe, again, without contact and without having to cut the sample. So these are some examples of imaging. Then on the spectroscopy side, we took several substances and we pressed them together into a pill. And then we developed methods to separate these different materials. This is something you can do with this kind of materials, such as talc and lactose, plastic like polyethylene, aspartame, like in this example. But you can also do it with other type of materials. So that would be in the second example with the Kepler card, where if you scan a corner there, you can look at the intensity image and you see some hidden features, a copper wire around the card, an RFID, a chip. And if you do a spectral analysis, you can also separate these different features. So these were some applications, and especially seeing the property that you can see through objects, it's actually quite natural to think that another application could be computed tomography. Computed tomography is known from X-ray, where it's already a rather well-established technique. And if we compare terahertz to X-ray, we can see a few aspects where terahertz could be a nice alternative to X-ray. For one thing, it's this low energy radiation, which is non-ionizing, so safe radiation. You don't need all the shielding for the operator that you need for X-ray. So that's quite a nice point. Terahertz radiation can also be used to analyze plastics, to do reconstruction with plastic samples, which is not so convenient in the X-ray. Then there are questions that arise compared to X-ray. The reconstruction problem with terahertz is nonlinear. You get some optical effects, such as refraction, that can complicate a bit the reconstruction. You also have a beam that is usually Gaussian shaped. So this is also something that has to be taken into account or at least considered. And last point, it's rather new. It's a technique that's still very much in development compared to X-ray, which is already a quite well-established technique. However, there are already some nice achievements, and I show a couple of examples that some may recognize. One is that we already saw some results with a high resolution and accuracy. For example, we demonstrated an accuracy better than 150 microns with our phase contrast CT. With other high frequency CV system, some show some higher resolution. And also systems that can do fast CT with single or few frequency systems. So on the right side, I show a couple of examples from other groups, from other people. On the top, this is a roll-it corrector that was reconstructed using a terahertz single frequency system in the rather low frequency range. This is a system that's advantageous if you want something that's fast and rather cheap. It has also a rather large field of view. On the bottom right, a really nice image of a tree leaf reconstructed using Lighted's imaging system. This is based on a high frequency optical terahertz source that can give you a fast and high resolution image. Then our approach in the PSSP project, we wanted to try something different. We wanted to do CT based on pulse radiation. This is not completely new, it has been done, but our idea was to, instead of exploiting the intensity information, which is what is usually done, we decided to exploit the phase information. That's why we called it the phase contrast CT. And then in a second part, we also integrated ray tracing simulations based on a priori knowledge of the sample that we had to increase the accuracy of the reconstruction. So on the right, you can see how our setup is built. TX is the terahertz source. We use special mirrors to focus the terahertz on an object that we want to reconstruct. In this case, for the scanning, we translated and rotated the object itself instead of the setup. It was simpler for us, although the other way around could be possible as well. Then the radiation that goes through the sample is focused on the detector Rx. And there you can see how the radiation looks like. So it's pulsed, very sharp peak. In black, you have the reference signal. And if you put an object in the beam, such as here in this example, polypropylene plate, you see that the signal is displaced and reduced. The reduction because some of the radiation is lost, so either absorbed or reflected, and there's displacement because you have a certain delay when going through the object. And when we exploit when we say we exploit the phase information, it's actually the information in the delay that we use. And the results were really, really nice. First results that we saw is a clear improvement when using phase information compared to an intensity-based reconstruction. So that you can see in the new image that just appeared. With this example, the sample that we used there is a 3D printed samples with a cylinder and the letter THz in it. Then you see the sinograms and the reconstructions based on the top on the energy, pulse energy, and at the bottom on the pulse phase. And you see really clearly that the pulse energy gives much worse reconstruction than the reconstruction based on the pulse phase. So that was already a very interesting result that we got. We tried different algorithms. So in these images, we used a filtered back projection algorithm, but we also tried other approaches for the reconstruction that for some gave a bit better results. But for this talk, I think it's enough to show this. Another thing that was interesting to look at is that when you look precisely at the image D there, the pulse phase reconstructed image, the cylinder is quite thin and the terahertz letters are broader, although when you look at the drawing of the letters with the dimensions on it, they should actually be comparable. This is because of something I already mentioned, refraction effects, especially when you cross a wall that is not straight, such as this cylinder. So this is something we actually worked on and could improve on using these ray tracing simulations. And with that, I will show some results on the next slide, but I can already tell you that using this approach, we improved the thickness determination and could reach a 150 micrometer, better than 150 micrometer accuracy. Although our source, which is broadband, has frequencies that are for the most part under 1 terahertz, so with a wavelength higher than 300 micrometers. So here are some of the results that we published. On the top left, you can see what happens if you have only straight walls. There, no ray tracing simulation was needed to get a high accuracy. We could estimate all wall thicknesses to about 100 microns. Then at the bottom, you see these two cylinders with two different reconstructions. The one to the left is the one when we use the ray tracing simulations, and the one to the right is what we get if we don't use ray tracing. So as you can see, the first cylinder is actually rather okay, the outside cylinder, but the inner cylinder, we used to have measured 2.5 millimeters instead of 2. And using the ray tracing simulation, we got much closer to the 2 millimeters. So mostly we measured 2.1 millimeters all around. Another interesting feature is if you look, there's one that's one measurement that's indicated in orange. That's kind of an outlier. It's a 2.35 millimeter instead of 2 millimeters. This is no artifact, it's real. It's actually a seam created by the 3D printer. And so it's nice to see that we could detect this defect using our method. Then on the right side, we wanted to see how good we could detect gaps, or let's say voids into a wall. And for that, we again printed two cylinders, one outer and one inner cylinder, and we left some gaps. The size of the gaps goes from 5 millimeters at the bottom to 1 millimeter at the top. On the top right, you can see the reconstructed image. And if you do a vertical slice through the face that has these gaps, you actually see quite clearly that all gaps appear in the image. And you can measure them. From 3 millimeters, you actually get a quite accurate measure of the gap size. Below 3 millimeters, you can detect the gap, but measuring it is more tricky due to the size of the Gaussian beam. So all these results have been published in Optics Express. If you want to have a look at them, at the bottom are the references. So with that, I quit the computed tomography, and I'm talking about another application that we developed for fast terahertz industrial system within another project, a new project called ATIC. In this project, we combine a fast, high-speed terahertz system with a robot. The high-speed system is the Teraflash Smart from Toptica, and the robot is from Phil in Austria. And with that, we showed that we could do real-time imaging of free-form objects and reveal some hidden structures. So I will start the video. There's no sound, no worry about that. So I'll start it. Okay, so in this video, as you could see, in these objects, we reveal hidden structures, in that case, letters, but the idea would be infinite to measure other things like defects or layer thickness. So that's one interesting application for non-destructive testing. There are others, so I will show a few examples of commercialized terahertz system especially for non-destructive testing that are on the market. On the top left is a system by Innox that can be used in extrusion line to measure the thickness of pipes in real time. On the top right is a Terahertz Scanner by TerraSense. So they have a 300 gigahertz source that they combine with a linear camera. And an idea of what you can do is to have a conveyor belt with objects running above the linear camera. And with that, you can measure in real time the objects on the conveyor belt. Bottom left, system commercialized by Hübner to do mail inspection. So this is terahertz spectroscopy with the aim of detecting mostly illicit substances like drugs or explosives. And finally, a THz-CT system does not exist yet. This is something we would like to see happening, of course. We are looking for key applications to enable the further development of the system and bringing on the market. So if you have ideas, there are suggestions, what could be interesting applications for these, we are happy to hear. So with this, I'm coming to the end of my presentation. Here I put my contact as well as Robert's if you want to contact us, if you have any questions. Thank you for your attention, and we can already answer some questions now, of course.
Thank you so much, Sandrine, for this talk.